There we go. So there's notation for array that we're going to need if we ever want to talk about this in writing. So if I wanted to represent this ray, this geometrical object, in words or in writing, I would write it like this. So it's something like the line AB, and to say it's a ray, I would draw a line with an arrow pointing one direction. Okay, so that's a ray. And in geometry, you might remember that angles are also very important. So an angle is, in mathematical terms, the union of two lines that share an endpoint. And when I say lines, it would be better to specify rays. So what does this look like? I might start by drawing 3 points, label them A, B, and C. So the pair of points A and B define a ray. So we connect them and then continue on. And then the 2 points A and C define another ray. And these two rays, let me go ahead and write their names. AB with an arrow and AC with an arrow. These two rays form an angle because they share an endpoint. And there's a few bits of terminology that we're going to need. So just like a ray had its own notation, an angle, we're going to write with a little angle symbol, and then write the 3 points that define the angle, and just go in clockwise or counterclockwise order. So CAB. And one important feature of an angle is where the endpoints meet. And this is called a vertex. It's a word that you'll see come up pretty often this semester. And there's lots more words that you're going to hear when we're talking about angles in geometry. Let's just talk about a few of them. When I talk about an angle, I might talk about an initial side and a terminal side. And I can make a little picture to explain what those two words mean. So here's an angle, two rays that share an endpoint. And what we want to think about for an initial side, usually we go in counterclockwise order. So I want to think about this as my initial side. And then I want to think about measuring my angle in this direction. So I start with the initial side and I go counterclockwise towards the terminal side. So terminal for terminate or ending. So initial is where you start, terminal is where you end. And angles also play an important role when we talk about circles. So just imagine I drew a perfect circle here. A central angle is an angle that has its endpoint or its vertex at the center of the circle. So we can just draw an angle here. Maybe make a note that this is the center. And that's where the vertex of my angle is. Okay. And when we start measuring angles, where the angle makes a segment of the circle, we have something called an intercepted arc. So an arc is a piece of a circle, and this is the piece that's intercepted by our angle. And other than circles, we often look at the two-dimensional XY plane when we're doing geometry. And this is related to the standard position of an angle. So we can just start by drawing the XY plane, like so. And an angle in a standard position is one that's centered, or it has its vertex at the origin. So let me make this line a little bit thicker to show that one of our rays is pointing in this way, this direction, along the x-axis, and we have another ray pointing off in another direction. So here we have the vertex at the origin. Any questions so far? Okay, so I'm just going to assume that you don't have any questions. If you don't speak up, and we'll move right along. Okay, so now that we have some mathematical language under our belt, we want to get kind of to the crux of the issue. In trigonometry, we're going to be talking a lot about degrees and measuring angles, and that's what's next on the agenda. A circle is divided into 360 equal arcs, and these arcs are what we call 1 degree. And if we want to talk about the degree of an angle, that's the number of degrees in the intercepted arc. So that's a bit of a mouthful, kind of a lot to take in when it's written down in words. So hopefully a picture will illustrate. So what we want to think about are angles in a circle. We want to think about central angles. So here's my vertex at the center, and well, an angle with 0 degrees would be like this one. So if it's 0 degrees, that means it doesn't have any degrees in its intercepted arc. So it's just straight. If I go a quarter of the way around the circle, say I make a vertical here, that means I go a quarter of the degrees. And 360 divided by 4 is 90. A 90-degree angle is up here. And one thing that you want to note as I'm saying this, when we're measuring angles, we almost always measure in this direction. So we start at a horizontal and to the right point, and then we measure counterclockwise. So if you're anything like me, you're probably wondering why there are 360 degrees and why we measure angles counterclockwise. And well, I don't think is a very good answer for that. This is kind of just the way mathematicians have been doing things, and people have been doing things for so long that we've forgotten why we do it. And well, we're going to do it the same way everyone else does it. I think there's some thought that the number of degrees, 360, is related to the number of days in a year, but you know that's not exactly correct, so who really knows? Okay. So we have the 0-degree angle, we have a 90-degree angle. If I go another quarter of the way around the circle over here, that means I need to go another 90 degrees, another quarter of the total degrees to 180. And if I go another quarter of the way, that's straight down, I add another 90 degrees and we end up at 270. Okay, so these 4 angles are probably the most important ones to remember. If you see these marked on a circle, you want to remember what angles these correspond to. And there's some more that you should be familiar with. Halfway between 0 and 90 degrees, we might want to mark in 45 degrees. So it splits the distance between 0 and 90, so it's half the number of degrees. And we want to think about the same angles over here. So I want to split the difference between 90 and 180 degrees. And this one is 135. So if you want to kind of see what's happening, I've gone 90 degrees and then I want to go another 45. So this 45 degrees splits a circle into 8 pieces. So if I go a quarter and then another eighth, I get to 3/8 of the circle. So you can count the slices I'm making, 1, 2, 3. And then there's the 4th one. If I want to make the 5th slice down here, I have to add another 45 degrees to get 225. And to finish off slicing my circle into 8 pieces, we come down here to 270 plus 45 again, 315 degrees. Okay, so those are some common angles because, well, they're simple. They divide a circle into 4 pieces or 8 pieces. You could also divide a circle into 3 pieces or 6 pieces, and it's probably a good idea to try to think through what that might be. So if you want to divide a circle into 6 pieces, you would divide 360 by 6 to get 60 degrees, and that would be somewhere here. And the picture in your textbook has a few more than I've drawn. Okay, so now that we've seen a few angles, let's talk a little bit more terminology. There's something called an acute angle. And these words have to do with the measure, the degree measure of the angles. Acute angles are between 0 and 90 degrees. And we think of these as small angles. So if you want to figure out a way to remember them, cute is, we usually think of something like a puppy or a kitten is cute and it's little, and there's small angles between 0 and 90. So here's an example. This one is about 30 degrees. A right angle is exactly 90 degrees. So these look like corners. And usually in geometry, when we talk about right angles, instead of putting an arc to represent the degree measure, we're going to put in a little box. Obtuse angles are bigger than both of these. They're between 90 and 180 degrees. Let's see, I just got a warning that my connection was unstable. Can you guys hear me?
Yeah.
Yes.
Okay, good. Okay, so between 90 and 80, 90 and 180, so they're large angles. If you start here, oops, you can't see what I'm pointing at. If you start here, you would need to go past 90 degrees into this region over here. So these are pretty big angles. And here's an example. This one is about 120 degrees. And next we come to straight angles. And straight angles, you probably wouldn't think of as angles at all. They are 180 degrees, and they look like lines. Okay, so there's the shared vertex for my two rays. I have one ray pointing to the right, another ray pointing to the left, and this is really just a line. So just like the line in the circle that splits it in two. Okay, and the final one, quadrantal angles, are kind of the oddball. They are angles where a terminal side is on one of the two axes. So if we're talking about quadrantal angles, we're talking about the XY plane, the two-dimensional plane. And here I have my vertex located in its standard position, and my initial side is pointing to the right along the x-axis. And then my terminal side needs to be on one of the other axes. So it could be, for example, down here. So here I'm thinking this is my initial side, so I'm measuring my angle the long way around this way. And thinking back to the circle, if we start facing to the right, and our other ray is facing down here. We know that this is going to be 270 degrees. Okay, so any questions about these angle ideas? Okay. I guess we must all be pretty comfortable with angles. So we'll move right along to what are called coterminal angles. Okay, so this might sound like a complicated idea because, well, there's this complicated term. Two angles are called coterminal if they have the same terminal side. But this idea is actually very simple once you start looking at pictures. And it also gives us an opportunity to talk about negative angles. So I said earlier that we measure angles counterclockwise around the circle. So if I'm starting here, I want to go counterclockwise. But if I want to go the other direction, say I want to start here and then go downwards, I would be talking about negative angles. So just like on the XY plane, I can go down here to my picture. This direction corresponds to positive along the x-axis. This direction corresponds to negative along the x-axis. Negative angles tell us to go the opposite direction. So if I start here with my initial side, and I go downwards in the clockwise direction to the terminal side, I'm going to get a negative angle. And this particular one that I drew, well, I guess it looks like it's minus 30 degrees. Wasn't exactly what I was going for, but close enough. And now let's talk about what a coterminal angle might be. So it needs to be an angle that shares the same initial side and terminal side. Let's label those. But I want to think about this as a different angle. So instead of going down in the opposite clockwise direction, I want to go in the old direction, the counterclockwise way, the long way around, like this. So if I go this way around the circle, this is actually going to be 330 degrees. Let's go back to that picture. So I'm trying to think of this angle down here in two different ways. So I want to think about going down clockwise around the circle or counterclockwise around the circle, but we still end up with the same terminal side. And this next statement here that I've written down helps us determine if two angles are going to be coterminal without having to draw a picture and just kind of guess from the picture. This gives us a concrete mathematical algebraic way of thinking about it. So let me just read it for you. The angles alpha and beta are coterminal if and only if there is an integer k such that this equation holds true. And let me explain what the M means. So remember, an angle we want to think about as two rays that share a vertex, share an endpoint. M of alpha, this is the angle, the measure of degrees. So M for measure of degrees. So alpha is an angle, it's a geometrical thing. M of alpha is a number, it's a number of degrees. And on the right-hand side, we have the number of degrees, or the measure of degrees for the other angle, beta. And then we see that's equal to k times 360 degrees. And k is a whole number. It's an integer, which means it can be a 0, or it could be a positive integer like 1, 2, and 3, or it could be a negative integer like -1, -2, or -3. So that feels a bit abstract. Let's try to make it more concrete by finding angles that are coterminal with 90 degrees. Okay, and maybe we want to start with a picture. Remember, a 90-degree angle, if we're thinking back to the circle, starting with a central angle, a 90-degree angle is one where the terminal angle is pointing straight up, the terminal side, excuse me. Okay. So I want to find more angles that look exactly like this one, but have a different number of degrees in them. And the way that I want to look at this is just by looking at this formula. So what I need to do is I take my angle 90 degrees, and then I add some whole number times 360 degrees. And then after we do that, I'm going to explain what it means geometrically. So some coterminal angles could be 90 degrees plus 1 times 360 degrees. So just doing the quick math there, 90 plus 360 is 450 degrees. We could have 90 plus 2 times 360 degrees. So 90 plus 720 comes out to 810 degrees. Okay, so what do those numbers mean? At the moment, maybe it doesn't seem like much, but what's happening here is this. So we have 360 degrees in our little formula here. And you might remember from a few minutes ago that the whole circle is 360 degrees. That's the whole thing. So if I start at my angle 90 degrees, if I add 360 degrees to that, that means that I'm going to go all the way around the circle. So all the way around and back to where I started. So if I start at 90, I add 360, I get 450 degrees. And then I could think about starting at 450 degrees, the same place, and go around the circle, the whole circle, again. And that adds another 360 degrees to get 810. And let's do maybe one more angle. Remember, k in my formula can be an integer. It could be a negative number. So maybe I could have -1 times 360. And 90 minus 360 that comes out to negative 270 degrees. So what is the minus sign? Remember a few minutes ago I told you that the negative angle tells you to go the other way around the circle, tells you to go clockwise. So I start at my 90-degree angle, and if I subtract 360 degrees from it, I go clockwise around the circle, all the way around, and I end up where I started. So this negative 270 represents going clockwise around the circle from 90 degrees. Any questions so far? Okay, so I guess I'm expecting most of you to have a good idea of what I'm talking about maybe already. But if you want to ask a question, maybe try to throw me a curveball or something like that. Maybe a question that you think will be challenging to answer. You could go ahead and ask me one of those. Or if you want to just continue listening, that's fine too.
Wouldn't you show the angles with like something in the middle?
The angles with
Like-
something in the middle?
Yeah, like a circle in the middle to show that it's gone around the whole circle.
Oh, okay. So maybe when I was explaining it, I could have, if I wanted to explain this, I could have started here and then gone all the way around like this to represent 450. And we could have kept on going, spiraling around the circle to 810. Yeah. So this spiraling is what we're doing around the circle. We're just keeping on going. Okay, so here is a question for our next example. Are negative 80 degrees and 640 degrees coterminal? So what I'm asking is, are they really the same angle in disguise? Have they really just gone around the circle a couple more times? So you could try to draw these angles, but I think you would run into some challenges trying to draw 640 degrees freehand. So we're going to go back to this little expression and try to use some algebra to answer this. So I know two angles are coterminal if I can find this number, k, this whole number k, where the two angles differ by k times 360. So I want to set up an equation. Okay, so on one side, I'll just pick one of my angles, minus 80, just the first one. And on the other side, I will put the other angle, 640 degrees. And then I need to have k, so k is my unknown, times 360 degrees. We need to see if we can find a whole number k to solve this. And we'll just do a little bit of algebra. We need to get k by itself. So the best way to do this would be to subtract 640 from both sides so that we can move this number to the left. Oops. What is 80 minus 600, minus 80 minus 640?
Negative 720.
Good. scroll down a little bit. So we have minus 720 on the left side. These cancel each other. So the only thing remaining on the right is k times 360 degrees. And to undo multiplication, we do the opposite of multiply. We divide by 360. And let me say for the record that it's not so much that I don't think you know how to do algebra. I'm just trying to explain it how you might explain it to a lower level class, like a high school class where you might want to work through the algebra a little bit. So I'm not trying to insult your intelligence. So let's just do this division. On the right side, this cancels out. On the left side, we have minus 720 divided by 360, and that will come out to minus 2. Okay, so we solved the equation. We see that k equals minus 2. Okay, so that's the answer to the equation. What's the answer to the original question? Are minus 80 and 640 degrees coterminal? Anyone want to answer?
Yes.
Yes. So what we were looking for here was a whole number. So the actual number itself doesn't really matter when we're trying to answer this question, just the fact that it's a whole number. That's all we need. So if we wanted to answer the question, we could say yes, minus 80 and 640 degrees are coterminal. Any questions? So let's talk for a second about quadrants. So quadrants are something that you would have learned about maybe in your Algebra 1 class, the first time you took algebra. And well, this is how they're labeled. We take the XY plane, the standard two-dimensional plane, and we label the segments that the axes divided into like this. So we start on the upper right, we label it 1, the Roman numeral 1, and then we work around counterclockwise. The upper left is 2, bottom left is quadrant 3, bottom right is quadrant 4. Okay, and something that you might be asked on a homework are, well, what quadrant does an angle end up in? So what quadrant is your terminal side in? So if I have a terminal side here, we would say the corresponding quadrant is 1. If I have an angle, let's say over here, so remember this is my initial angle, that's my terminal angle, so that would put it in quadrant 3. And that's just the general idea. If you have a terminal side up here, it's quadrant 2. Terminal side down here, it would be quadrant 4. So just something to keep in mind, since you might see those words on your homework. And then the last idea that we're going to talk about today is this one. So some of the time we might need to talk about small angles, or maybe we need to talk about very small differences between angles. And in order to talk about those, we're going to need to have this idea of minutes and seconds. So these are really old ideas. I think they were used way back in the day when people were navigating on the ocean using the sun. And they had this idea of minutes and seconds to divide up angles so they could figure out, where they were on the planet. but we also use them here in our trigonometry or geometry class. And let's just talk a little bit about what they are. A degree, a single degree, is divided into 60 equal pieces, and we call each of those pieces a minute. And if we want to talk about even smaller divisions, we can take our minutes and divide them into 60 more pieces to get seconds. So if you want to remember how minutes and seconds work, they work exactly the same way minutes and seconds do on the clock. An hour is divided into 60 minutes, and a minute is divided into 60 seconds. So just like that, also for degrees. So a degree is divided into 60 minutes, and a minute is divided into 60 seconds. And down here, I've written a few things that might be helpful a little bit later on, because we're going to have to be able to convert between minutes and degrees and seconds and minutes and that sort of thing. So you might need to remember that there are 60 minutes per degree. And if we flip that around, that means there's 1/60 degrees per minute. And the same kind of relationship goes for minutes and seconds. And I want to add one more row. So if there are 60 minutes per degree and then 60 seconds per minute, that means that there are 60 times 60 seconds in each degree. So there's actually 3,600 seconds per degree. And flipping that around, that means there's 1/3,600 degrees per second. So these relationships will come in handy in just a minute. Oh, I guess I should see if you have questions before we move on. Any questions? Okay. So let's move on to the last few pieces of the lecture. We're going to do some examples where we have to think about the relationships between degrees and then degrees in minutes and seconds. And the first thing that I want to do is talk about converting an angle measurement. That was a new one. An angle measurement that uses degrees, minutes, and seconds to decimal form. And I've written a couple things there that I haven't explained yet, but I named them as I was writing them. So you already know this symbol. This little circle means degrees. This symbol, well, you might have seen it talking about time. This symbol, it's one single apostrophe. That refers to minutes. And the double apostrophe, also known as a quotation mark, that refers to seconds. So this is 30 degrees, 30 minutes, and 12 seconds. But what I want to do is take this way of writing things and try to convert it to a decimal number using just degrees. And let's just walk through how to do this. Step one, will be to convert minutes to degrees. So I have 30 minutes, and I'm going to use the relationship that we just finished talking about to convert it to degrees. So I know there's 1/60 degrees per minute. So that's what I'm going to multiply in order to convert to degrees. I'm going to multiply by 1 degree per 60 minutes. So the idea here, I'm sure you've seen how to convert between other kinds of things like feet and meters or seconds and hours. We look at the units of measurements. We have minutes. It cancels off with minutes in the denominator. And then we just are left with numbers and degrees. So multiplying 30 times 1/60, we get 30/60. And then degrees. And we'll do the same kind of thing to convert the seconds, the 12 seconds, to degrees. So we start with our 12 seconds. And then we use the relationship from a minute ago. We know that there is 1 degree for every 3,600 seconds to convert. So the seconds disappear, and we're left with these numbers that we need to multiply to get 12 over 3,600 and degree. Okay, and we're pretty much done. We just have to add these two fractions to our 30 degrees. So we have 30 degrees, and then we need to add 30/60 degrees for our 30 minutes. And then we need to add 12 over 3,600 degrees for our 12 seconds. Let me just write out that expression. This original number is equal to 30 plus 30/60 plus 12 over 3,600 degrees. Okay. And if we were really ambitious, we could convert our fractions into decimal form using long division or something like that. Or if we were lazy, we could enter it in a calculator to get a decimal. And this is what it comes out to, 30.503 degrees. And this 3 here is actually repeating, though in most cases we would probably just round to some finite precision. Okay. Any questions over how we converted this measurement into a decimal number? so I guess not. I'll leave that up there in case you're still writing while I write down the next example. So we converted degrees, minutes, and seconds into a decimal form. I also want to be able to go the opposite direction. I want to be able to start with a decimal form and then convert into degrees, minutes, and seconds. So let's try that out. We'll convert this number 44.235 degrees to degree, minute, second format. So there's also a strategy here. It's essentially the opposite of what we were doing before. We want to convert the opposite direction. And we'll start by converting, or let me step back just a second. We want to leave the whole degrees alone, because these are whole degrees, and this fraction, this decimal part, is what we'll need to convert into the smaller measurements of minutes and seconds. So our first step is, well, to ignore this, 44, and convert this decimal part, the 0.235, to minutes. Okay, so the decimal part is 0.235. That's in degrees. And we know there are 60 minutes per degree. So I'm going to use that fact to convert. I'm going to multiply by 60 minutes per 1 degree. So we're doing exactly the opposite. We flipped the fraction. Let's see, I just got a warning that my internet connection was unstable. Can you guys hear me?
Yes,
Yeah.
sir.
Yeah.
Okay, thank you. Okay, so the degrees cancel. We just have to multiply 0.235 by 60 over 1, and then we're left with minutes. And I'm just going to tell you what the answer is here. You might want to use a calculator for this. It's 14.1 minutes. Okay, so what do we have now? We have 44 whole degrees, and we have 14 whole minutes. And what's remaining to convert is this 0.1. I want to convert this other decimal part of minutes into seconds, my next smaller form of measurement. So we do the same thing. We convert the decimal part but now we're not converting to minutes, we're converting to seconds. Okay, so now we have 0.1, 0.1 seconds, 0.1 minutes. And we know that there are 60 seconds per minute. So we take our 0.1 and we multiply by 60 seconds per 1 minute. It works out just like before. The minutes go away and we're only left with seconds. And we have to multiply 0.1 times 60, which gives us a whole number, 6 seconds. Okay, so walking through, we have 44 whole degrees. And then we saw that we had 14 whole minutes. And then finally, we ended with 6 whole seconds. And we can end by writing down the conversion. 44.235 degrees is equal to 44 degrees, 14 minutes, and 16 seconds. Any questions before we move on? I think we'll do one more example. And then maybe talk a little bit. So to wrap up here with another example, I want to add 2 degrees or 2 angle measurements, but my angle measurements are going to have minutes and seconds in them. So I'm going to start with 10 degrees, 24 minutes, 43 seconds. And I want to add this to 24 degrees, 38 minutes, and 30 seconds. And what I want to do is, well, add these 2 and also try to simplify my answer. And I'll explain what I mean by simplify as we work through. And the way that we add these together is really just like normal addition. In fact, we can even stack them on top of each other, like you might have learned to add numbers way back in elementary school. And we want to think of the minutes, seconds, and degrees as place values. So back in elementary school, you probably learned to add your ones together, you add your tens together, you add your hundreds together, and so on and so forth. And I know it's a little bit more complicated than that, and I know there's new teaching styles out there for addition, but let's just go back to that kind of basic idea of adding place values. So I want to add my seconds together. 43 seconds plus 30 seconds gives me 73 seconds. Let's see, waiting for my connection to clear up, it looks like. Okay, so we get 73 seconds. We add 24 minutes and 38 minutes to get, what is this, 62 minutes. And then we add the degrees together. We have 10 degrees plus 24 degrees to get 34 degrees. So we could stop here, but what I want to do really is simplify this a bit. And what I mean by simplify is that I have, for example, 73 seconds here, but 73 seconds actually adds up to more than a whole minute, because I have more than 60 seconds. So this is something like carrying a 1 when you are back in elementary school doing place value. So if you add 2 numbers and you get something bigger than 10, you know you have to carry a 1 to the next biggest place value. So if I get something bigger than 60 here, I have to carry a minute up from my seconds. So I subtract off 60 from this. This is really, what, 13 seconds, and then I carry a 1 over here. But 62 plus 1, 63 minutes, that's also bigger than a whole degree because it's more than 60. So I have to think about carrying another 1 up to my degrees. So I take 60 of these, move them up here. I have 3 minutes left. And then 34 plus 1, 35 degrees. And this is where we really want to stop in a kind of simplified form for our angle. Okay, so that's where I'm going to stop today. Does anyone have questions? Okay, I guess not. What do I want to do now? So there were a few more topics that I could have fit into this section, but you kind of have to pick a stopping point somewhere. We could, for example, subtract numbers or multiply, things like that. But let's just stop with addition. What I want to talk about for the last 4 or 5 minutes of class are just what you think about the teaching style. What did you like? What could use improvement? What might you use in your own classes? And feel free to be harsh about it. I kind of made this one as simple, a lecture format, a straightforward lecture. And I know lots of people don't like lectures. So just go for it. What do you think?
I mean, there's definitely pros and cons to like doing this type of style.
Mhm.
Mostly because the fact that it really doesn't like encourage the student to like take notes or whatever. I mean, technically we write down examples, but like our definitions are already there and stuff, and we don't necessarily have to do anything. Like,
Okay. So do you think making the students write down the definitions, do you think that'll help them learn the definitions?
I mean, for me, writing it down makes me remember them better.
Mm-hmm.
Where reading it doesn't exactly do that for me, but that's just my learning style.
Okay. I definitely understand what you're saying. I kind of completely agree with you. Do you think that would work in this format, in the Zoom format, making you take all of the notes from the Zoom video? And someone else can answer if you want to.
I think it would work. I mean, I like the pre-written notes because I think that like working out problems is more important than definitions in math class. But I mean, I took all these notes myself, so I
Okay.
mean, I think that it's doable, and I have from my other classes as well. So
Okay. So your other teachers do something similar. They just kind of makes you write down the whole notes. Okay. Um, let's see, where can we go from there? Oh, you mentioned something that you think practicing problems is how you learn math. Could you maybe elaborate on that?
I think that with math class, the most important thing is the repetition of it. I mean, it's pretty much how you learn to do any skill, and I feel like that's probably the most important part of the class in most classes, at
Okay.
least. I feel like the terminology kind of sticks along with it, I guess.
So if you practice doing something, the language kind of comes naturally. Yeah.
Yes, sir.
Okay. Um, so the way I like to think about math is that it's pretty similar to learning how to play an instrument. You might notice a couple guitars behind me. Um, it's similar to learning an instrument or learning a sport. You kind of learn how to do it by doing it, by practicing. I definitely agree with that thought. Alex, do you have anything to add here at the end?
Yeah, like so I kind of agree like having some of it filled out can be nice, but at the same time with having some of the notes already filled out, it gave at least me and I know other students that have had the issue of like time to distract themselves. Like it's just at least for me it's harder for me to like continue to stay attached to the lecture if I'm not like constantly having to write stuff down. So like
Mhm.
finding a good balance is always really nice of not writing too much but writing enough to keep me intact paying
Okay.
attention.
So maybe I could improve my note outline by leaving more blanks, like in the definitions and things where you have to fill stuff in. You think that would help?
Pers-
I think
Personally
that
I
would
would
work really
prefer,
well.
yeah,
Okay.
more blanks is what I would like.
Hmm.
Yeah, I like that idea. Okay. So it looks like we're right at the end of class, 6:46. So we can stop our discussion there. Um, so on Monday, I'm going to try a different teaching style. I haven't completely worked out what it'll look like, but it'll be ready on Monday. And in the meantime, make sure that you are working on the blog post about your own experiences in math classes. And other than that, I'll see you next week. And I can stick around a few minutes if you still have questions that you want to talk about or anything else you want to talk about.